Hello students, have you ever wondered why water bugs can walk on water without sinking? It's like the water has a tiny invisible skin holding them up, and that's exactly what surface tension is. Now, why did the water molecule break up with the air molecule? Because it felt two asterisk wrapped up asterisk in its own surface. Surface tension arises because molecules at the surface of a liquid stick together more tightly than those inside. See, molecules inside the liquid get pulled equally in all directions by their neighbors, but the ones on the surface have neighbors mainly beside and below them, creating an inward pull. This inward pull effectively pulls the surface molecules together, making the surface behave like a stretched rubber sheet. We define surface tension as the force acting along a line on the surface, pulling perpendicular to that line. In other words, surface tension T equals force F divided by length L, so T is equal to F over L, measured in newtons per meter. This is why, without any external forces, liquids form spherical drops, because a sphere has the smallest possible surface area for a given volume, minimizing the energy stored in the surface. So, next time you see a drop of water, remember it's nature's way of saving energy through surface tension, creating a tiny liquid ball. Let's think about surface tension from an energy perspective now. Imagine molecules on the surface of a liquid as guests at a party who have less fun than those inside because they're more exposed. This means surface molecules have higher potential energy than those fully surrounded inside. Increasing the surface area is like inviting more guests to a crowded party. Work must be done to stretch the surface against the cohesive forces holding molecules together. This work done increases the surface energy of the liquid. Mathematically, surface tension equals the work done to increase the surface area divided by the change in area. In other words, T equals W divided by delta A, where W is the work done and delta A is the increase in surface area. Both surface energy and surface tension share the same units in the C system, newtons per meter, or equivalently joules per square meter, linking force concepts with energy. Imagine a liquid film expanding. It resists stretching because each bit of area added costs energy, just like stretching a rubber sheet. This link between force and energy is what really unites the concept of surface tension in physics. Now, what happens when a liquid meets a solid surface? Think of water trying to stick to glass or mercury refusing the same. This interaction is measured by something called the angle of contact, theta, which is the angle formed where the liquid surface touches the solid. It depends on two forces, cohesion between liquid molecules and adhesion between liquid and solid molecules. For good wetting, like water on clean glass, this angle is less than 90 degrees, meaning water spreads nicely. But for poor wetting, such as mercury on glass, the angle is greater than 90 degrees, so mercury beads up. The balance of these surface tensions is captured in Young's equation, which says that the surface tension between solid and gas equals the surface tension between solid and liquid plus the surface tension between liquid and gas times cosine of theta. Formally, T sub Sg equals T sub Sl plus T sub Lg times cosine theta. This is why detergents work so well. They reduce the liquid-gas surface tension, T sub Lg, changing the contact angle and making liquids spread better. Next time you see soap suds cleaning your hands, remember it's all wetting agents and surface tensions at work. Here comes one of the coolest phenomena in surface tension, capillary action. Ever noticed how water creeps up a thin straw or how plants drink water from the soil? That's capillary rise caused by surface tension pulling liquid upward in narrow tubes. Let's break it down mathematically. The height h that the liquid rises equals to times surface tension T times cosine theta, the angle of contact, divided by the product of the liquid's density ρ, gravitational acceleration g, and the tube's radius r. So, h equals open bracket 2 times t times cosine theta close bracket divided by open bracket rho times g times r close bracket. The physics here is a force balance. Surface tension pulls the liquid up while gravity pulls it down with the weight of the liquid column. You can visualize this in a narrow capillary tube where the curved meniscus forms an angle theta with the tube wall, radius r is labeled, and height h measures how far the liquid climbs. Notice that the rise height increases as the tube radius gets smaller, making capillarity very effective in tiny tubes. This principle is even used in thin tube viscometers to measure fluid properties. Nature truly masters tiny engineering. Surface tension isn't a fixed number, it changes with conditions like temperature and impurities. When temperature goes up, surface tension goes down because molecules dance faster and intermolecular forces weaken. Empirically, surface tension T at temperature T equals T0 times open bracket 1 minus K times T close bracket, where T0 is the surface tension at 0 degrees Celsius, K is a constant specific to the liquid, and T is the temperature in degrees Celsius. So, as temperature rises, surface tension decreases almost linearly for many liquids. Impurities also play a big role. Soluble impurities like soaps and detergents reduce surface tension, helping liquids spread and clean surfaces efficiently. On the other hand, organic impurities such as oils often increase surface tension by forming sticky layers that strengthen intermolecular attractions. Imagine a graph showing surface tension decreasing as temperature increases. This captures why hot water feels wetter than cold water as it spreads more easily. Ever wondered why soap bubbles are fragile yet keep their shape? This is explained by the pressure difference across curved surfaces caused by surface tension. When a liquid surface curves, pressure inside differs from outside because surface tension resists expanding the surface area. For a spherical liquid drop, the excess pressure inside compared to outside equals to times surface tension T divided by the radius r, that is, delta P equals to T over r. However, a soap bubble has two surfaces, an inner and an outer skin, so its pressure difference doubles to 4 times T over r. You can picture this in the diagram showing a spherical drop with pressure arrows pointing inward and a bubble with two curved surfaces, each contributing to the pressure. This pressure difference explains why bubbles are stable and why droplets form discrete spheres. It's even exploited in ultrasonic cleaning where tiny bubbles scrub surfaces with pressure pulses. Surface tension really packs a punch. Let's put theory into practice with a quick example calculating capillary rise for water in a glass tube. Given surface tension T equals 0.072 newtons per meter, radius r equals 0.5 times 10 to the power minus 3 meters, density ρ is 1000 kilograms per cubic meter, gravitational acceleration g is 9.8 meters per second squared, and angle of contact theta is 0 degrees since water wets glass fully. Using the formula, height h equals open bracket 2 times t times cosine theta close bracket divided by open bracket rho times g times r close bracket. Substituting the values, h equals to times 0.072 times cosine 0 degrees divided by 1000 times 9.8 times 0.5 times 10 to the minus 3. Calculating cosine 0 degrees gives 1. So numerator is 0.144 newtons per meter, denominator is 4.9 times 10 to the minus 1. Dividing, we get h equals approximately 0.293 meters or 29.3 centimeters. This tall rise is typical in narrow tubes and matches observations perfectly. Picture a thin glass tube with water climbing almost 30 centimeters, capillarity in action. To wrap up, surface tension is a fascinating property where the force per unit length on a liquid surface, T, equals force F divided by length L and also equals work done divided by change in surface area. We saw how capillary rise height h depends on 2 times surface tension times cosine theta over density times gravity times radius, and how pressure difference delta P equals to T over R for droplets and 4T over R for bubbles. Temperature increase generally lowers surface tension, while impurities can either lower or raise it depending on their nature. Surface tension explains why drops form spheres, why liquid climbs narrow tubes, and why bubbles hold their shape. So next time you see a drop of rain or soap bubbles, remember the tiny molecular forces playing big roles. That's all for today's lesson on surface tension. Physics is more fun when you laugh and learn. See you in the next class.